All right, folks, welcome to 6-4. 6-4, we're going to look at a cross section and some longitudinal sections of bone and compare and contrast dense bone and cancellous bone. All right, so a lot of this is lab stuff because you had to look at this model in lab. And you can see here that we have some compact bone. That's everything from here outward. It's compact bone. And then here we have spongy bone, and that's the medullary area, the medullary cavity of the bone. And the epiphysis, remember, is mainly just spongy bone, whereas the diaphysis of long bones is the periphery or the circumferential area is compact, whereas the medullary cavity is spongy. So let's look at the compact bone first. This is called an osteon. These repeating circles are called osteons. And the osteons are all built the same way. And what they have is a central canal with a nerve, artery, and vein, and sometimes lymph vessel. And then each central canal is surrounded by concentric circles of hard bone, lamella. These are called concentric lamella. Now there's a problem, and the problem is when you put circles together, you have spaces in between them, by definition of those being circles. So what do we have in between these circles? We have interstitial lamella filling in these areas in between the circles. That's interstitial lamella. And then likewise, when you have a periosteum surrounding your whole bone, and you have these circles, you also have these spaces between the circles and the outer layer, the outer periosteum. And what fills that in is not called interstitial lamella, but it's called circumferential lamella. So we have circumferential lamella and we have interstitial lamella by virtue of the osteons being circular, and circles don't fit well together. So we have this lamella, which is the hard bone. And we're going to look at the collagen fibrils in the lamella in a few minutes to show you something that probably will surprise you. This part of the picture right here pulls the different lamellar layers up and out so you can look at them, and you can see the central canal containing the artery and vein, and you have the first concentric lamella and the second concentric lamella and the third concentric lamella. You can see that. And then if you did a longitudinal slice of the bone, you would see that my central canals of one osteon are connected to the central canal of another osteon. And these are called Volkmann's canals, by the way. Let me get it over here. That's called a Volkmann's canal. So my central canals are connected by Volkmann's canals, also known, by the way, your book will probably say it this way, perforating canal. So your book will call Volkmann's canals perforating canals. All right, so that's about it for that. We are going to look at the cross-section of trabeculae, which is a spicule, a bony spicule found in spongy bone. We're going to look at that. But I first wanted to show you the osteon system. These osteons it's how we make up dense bone or compact bone. Now this is really cool. When the osteoblasts lay down the osteoid, it's mainly collagen. All right, so collagen is a triple helical protein. That means there's 3 alpha helices all intertwined, and that's just one collagen molecule. That's a triple helical protein molecule. And when the when the osteoblasts lay down this collagen, you'll see that in one of the concentric layers, you'll lay down collagen running from, say, top left to bottom right. And you'll see them going like that. And then in the next concentric layer, the collagens will be laid down running from top right to bottom left. Or if you wanted to say from bottom left to top right, it wouldn't matter. Just be consistent of what you say top and bottom. So start with the top. This first concentric lamella is top left to bottom right. The second one is top right to bottom left. The third one is top left to bottom right. And by doing this adds a lot of strength to the bone, because now these collagen fibers are going to be able to withstand stresses from different directions. And that makes the bone quite a bit stronger with these collagen running in different directions. All right. Spongy bone is made up of trabeculae. You can see all of these trabeculae in here. Look at all this stuff. Now, the thing with spongy bone is this. It's strong because the trabeculae are running in all different directions. So they can dissipate the weight or the stress through different trabeculae in all different directions. So they're strong, but they're light. So they're strong and they're light. And if you look at one trabeculae, you see the endosteum is surrounding it. Well, that makes sense because most of my spongy bone, well, yeah, that's fair to say. Most of my spongy bone is inside my medullary cavity. Why wouldn't it have an endosteum surrounding it? It does. And then you can see the lamella in here. Now you see lamella in here, but you don't see an osteon. There is no central canal with a nerve, artery, and vein. There is no Volkmann's canal. So you don't see osteons, but you do see lamella. Of course, trabeculae are made of lamella because that's how we make bone. We lay down these layers of collagen and then calcify it. So there's lamella in my trabeculae. There's just no osteons. All right. This is looking at force being applied to a bone. And what it's telling you is this. When you're in dense bone, you're pretty much, the force is a pretty linear distribution of the force because it's dense bone. Now, yes, the collagen is running in opposite directions, and that does allow that bone to withstand forces from different directions. That's true, but it's pretty dense bone, and I'm not going to spread that force out a lot at this point. But as I go from dense bone down into spongy bone, now I'm ready to spread this force out because my trabeculae, one trabeculae will take on part of the force, the other trabeculae take on another part of the force, another one another part. And these trabeculae, let me go backwards now. These trabeculae are running all different directions. So if the force was coming down through here, the force would be spread out that way and that way. And if there's one back behind the screen, that way. And then where does the force go? Well, it goes here, and then it goes this way and this way. And you can see we spread out the force. So now when you're talking about where is that force, well, it's spread out amongst different areas of the bone. It's not just one area. Now, having said that, I have read, and this is kind of cool. Actually, I'll save and tell you that during the joints. During the joint chapter, I'll tell you what I was just about to say. So that's applied force on a bone and showing you how we can spread the force out. By the way, I don't like how this one red line came down onto one side of the bone. I wish they would have spread it out over here, because likely it probably is. I mean, these are trabeculae up here too. So likely this applied force here probably went over here as well, not just this one side of the bone. All right. So that's force applied to a bone. Now, we already talked about where these cells are located. We said that the osteogenic cells are located underneath the periosteum and scattered throughout the endosteum. So if you look at the endosteum here, which we are, and you blow it up, you can see that you have osteoclasts scattered throughout the endosteum, and you see this osteoprogenitor cell scattered throughout the endosteum. So we have these cells underneath the periosteum over here. I'm looking over here now. So we have some of them over here, and we have them scattered throughout the endosteum right here. You blow it up and you can see that. So that's where they're located. The periosteum and the endosteum are made of dense irregular connective tissue. That's what they're made of. The periosteum is a complete layer, and the endosteum is an incomplete layer. And actually, what I wish was showing you here is from the periosteum to the bone, these red lines I'm drawing right now, are these fibers called Sharpie's fibers, and they really hold that periosteum tightly to the bone. And in fact, what we think shin splints are is tearing of the periosteum away from the bone of the tibia. And because of those Sharpie's fibers, that's a very painful event, and that's what we think shin splints are. What we call shin splints. And you might say, well, it's 2016. Don't we know what shin splints are yet? Well, Maybe, maybe not. Maybe we're right and maybe we're not. But just think of this. When you x-ray a bone like that, you're only getting this compact stuff with minerals in it. You're not getting the soft tissue. So x-rays are tough to tell. But there's other imaging techniques, and what we think is that shin splints are the pulling away of the periosteum. All right. That's it. Next section coming up.